Okay, I think we're ready to start. And what we'll do is that before we pass on to the test, we'll have sort of short presentations. It will start with myself to present to you a little bit about, tell you a little bit about Eucentre. For those of you who do not know Eucentre, for a number of you instead will be perhaps more of the same, but hopefully not. Hopefully there will be elements of novelty also for those of you that know Eucentre very well. Then, so that will be myself for 2 minutes. Then Professor Calvi will talk a little bit about the design of this test facility. And then we will have Dr. Igor Lanese, Vice Director of the laboratory, that will be describing the test itself. So let me see if I can see there's some difficulties with the presentation, because I should have some slides on Eucentre coming on here, but they're not there. So let me see if Marco can help me out, or if Andrea can help me out. Yeah, there you go. Okay, so here we go. So we're here. You can see we are in front of that building that is on the far right. There you have the square that is empty now. It's obviously we have these seats where you find yourself right now. So what is Eucentre? Eucentre is a private foundation, a non-profit organization that is actually being created by 4 public institutions that you see listed there. So the Italian Civil Protection, the Italian Geological Survey, INGV, National Institute for Geophysics and Volcanology, and the 2 local universities. So Eucentre is a private entity that has been created by 4 public institutions. And in addition to that, Eucentre is what is called in Italy as a center of competence of the civil protection, with a number of duties, as it were. And so the first one is that of developing tools that allow the civil protection to assess risk pre and post event. And to do this, Eucentre has developed, on behalf of the civil protection, of the Italian civil protection, quite a large collection of databases. And these databases can be on buildings, so buildings aggregated information on buildings on all the municipalities in Italy, as well on critical buildings like hospitals and schools, as well as in infrastructure like ports, airports, bridges, road networks. So with this kind of information, Eucentre has built a platform that allows the civil protection at any moment in time to do damage scenario assessment, or after an event, the civil protection receives automatically a message generated by Eucentre systems that provides the civil protection with an estimate of the impact of that earthquake, including road viability. So the civil protection knows that in order to reach to the most affected areas, it is better not to use certain roads, certain bridges, because the damage estimates tell them that it is likely that they will not be usable. So that's one of the activities of Eucentre. Another one is to help the civil protection in managing situations post-event. And in particular, those 3 there that you see listed is where Eucentre has been the most active. They're also the more significant ones over the past 20 years or so. And one of them is assessing damage right after an event. So the use of automatic image collection and automatic image processing to assess damage. But also, wait a second, I just went a little bit too far. Also, the reconstruction of, or if you will, the housing of displaced people. This is after the 2009 L'Aquila earthquake, where there were 15,000 displaced people that needed to be housed in, and the desire was to house them in safe and not necessarily temporary houses. So not necessarily tents or sort of barracks or containers, but actually safe houses, base isolated houses to pass a message of safety and as comfortable as possible. And the challenge there was to build these 185 seismically isolated buildings in 9 months. So this was the largest construction site ever in the world. The whole construction was coordinated and managed by Professor Calvi with a large team that was monitoring this on a 24-hour basis. They were doing turns of 8 hours, 3 turns of 8 hours a day, and this was really something else. And these buildings, these seismic isolated buildings, 15 years on, Eucentre went there to test if these curved surface sliders, isolators, were still working as they should be, and notwithstanding the fact that there was not really a lot of maintenance or any maintenance at all. So 15 years on, this is obviously a building, one of those buildings that is not currently being used, and so it was possible to do the test. 15 years on, these isolated structures are still working. But it's not just a question of displaced people. It's also when it comes to reconstructing damaged, in this case, villages. So this is Arquata del Tronto. Arquata del Tronto, as you can see there with the picture on the left, was a very picturesque cultural heritage borgo village in Italy. And as you can see with the sad image on the right-hand side, after the 2016 Central Italy earthquake was severely damaged. And now, for a number of reasons that it's not here, this is not the right place to discuss, but for a number of reasons there is a desire to reconstruct it, to bring it back to what it was. And so again, as usual, Professor Calvi, the president, is actually the founding president of Eucentre and now the president emeritus of Eucentre, was asked to give a help, and Eucentre was involved in this. And one of the first things that had to be done was to render the hill safe, so that in case of further future events, that the hill would maintain its stability. And so this was done by using this process of introducing these ties that you see there. You will see them even better in this animation. This is an animation that comes from the bottom upwards. And you'll see as we go from the bottom of the hill upwards, you'll see all those ties. And so these cables that sometimes go from side to side of the hill that keep the hill together. And this was the first step. Obviously, when you do this, you create this very rigid body that will then cause the accelerations at the base of the buildings on the top to be extremely high, which means that when you then want to reconstruct these buildings, you actually need to make them base isolated. And so what Eucentre is doing now is to coordinate the process of designing, or if you will, to pave the way, to open the way of the process of designing seismic isolation for each one of these buildings. The problem is that, as you can see there, they're not really sitting on a plate by themselves. They are a very complex, they have very complex aggregate configuration. So these are buildings, aggregated buildings that go on steps. And so you can imagine a system of plates, of platforms, of slabs, continuous, that allow this base isolation of these buildings, and you can imagine it's definitely not something particularly simple. But if it was, then they would have not asked us to do it. So that's what Eucentre is here for, is try to address these kind of more challenging problems. Now, in addition to that, as part of being a competence center for civil protection, we need to carry out lab testing for vulnerability assessment and mitigation. And I will not show you a lot of tests, but I'll just show you this one, because this one, maybe this one and another, just to show you that in one of the, in our other shake table, it's not this one, it's the biggest shake table that we have on the other building, we've actually built a bell tower inside. It was a very important project involving all sorts of very important stakeholders, including, as you can imagine, religious stakeholders. And the idea was to test this bell tower in full scale. And you didn't see much of a shaking. The one on the left doesn't have an active mass damper turned on. The one on the right does. What I'll show you now is the zoom at the top of that bell tower. And when I show you the zoom, you'll notice that the one on the left, the one without the active mass damper turned on, shakes much more than the one on the right. So you'll see the one on the left that is going to vibrate much more. The PGA is relatively modest, but still enough to get this bell tower to have a significant movement. The one on the right didn't move much, but you saw the active mass damper moving instead. I'll go back and I'll go on again. Now look at the one on the right, and you'll see the active mass damper that is moving on the right, and therefore it's making the bell tower stand still. But we don't test just buildings or structures. In this shake table here, we also test equipment. This is a generator that is supposed to work after an earthquake, because otherwise it would not serve its purpose. And so after this very intense shaking of this generator done on this table here, we actually had to turn it on to make sure that it worked after the shaking. It did work, so the test and the certification was a success. So finally, one of our our final fourth main mission under the framework of being a competence center for data privacy and protection is training and dissemination. And we are very lucky to partner with IUSS of Pavia and the University of Pavia to run a series of postgraduate programs, 3 different postgraduate programs, and that have welcomed students from 60 countries, from around the world. Over the recent years, we also see a very important involvement of the GEM Foundation in these activities. As I said, it's not just training, it's also dissemination. So always for the Civil Protection Department, we develop a platform where any citizen in Italy can go, enter this platform, and have an information on what's the risk of their municipality. Of course, we had to involve experts in communication to communicate the risk in a way that the non-expert members of society can understand it and can deal with it. We don't want to cause any alarm, obviously. And loads of events to raise risk awareness around Italy. This is my last slide, just the year 2025 in numbers. And the reason why I showed you this is, and that's the message that I wanted to leave, as you can see, it's my last slide, my final slide, is the first line there. So we are a research center. Our funders are 4 public entities, but as you can see there, we've carried out 100 applied research projects for the private sector. And this answers also to some of the questions that were being raised now in the session about the engagement of the private sector that Gerard was raising again and again. If you don't engage the private sector, an organization like this one that does not have any ordinary funding, that is, we receive €0 from the state. Every single euro in that overall budget that you see at the bottom needs to be earned. It's not guaranteed from year to year. If you don't have the engagement of the private sector, we cannot operate. And again, as Gerard was noting, it is through the engagement of the private sector that we also understand what are some of the problems that need to be solved. And so this is just to exemplify the kind of thing that Gerard was talking about earlier on. Okay, as I promised, this was my last slide. I will now pass it on to Professor Calvi, whom, being Professor Calvi, obviously is not going to use any slides because he doesn't need any support, any assistance from PowerPoint. He does it all out of his own brain, unlike myself. Michele, thank you.
It's for me, not for him, right? Well, as Rui pointed out, Eucentre is a relatively young institution. And about 30 years ago, one could have been thinking of what would have been the best way of creating a new testing facility. You may remember, some of you, the oldest one, that in Japan there was a well-known professor, Koichi Takanashi, who had just invented the pseudodynamic testing method, which was somehow diffused at Berkeley by Steve Main, who used it extensively and made it more popular. And in Europe, it was the testing method used at ISPRA. There was Jean Donneau, who was the chairman of the ELSA facility. There was Guido Verzaletti. There was Magonet, and so on and so forth. So one could think, well, we could have a facility where we are going to use pseudodynamic testing. On the other side, from my point of view, most of the shake tables that were available at the time were not really suitable for seismic testing. Too small displacements, velocities were not enough. The only one that had some decent performance was a rather newly established one in San Diego with only 1 degree of freedom. But the one, for example, at Berkeley or the previous one at Urbana were really, really not interesting from a seismic point of view. So when we started with this facility, the first thing that we created was a very powerful shaking table, 1 meter displacement, 2.2 meters per second velocity, 7 point something G acceleration capacity. We could run anything. Side by side to that, there was a reaction facility with 3 sides, 2 strong walls and 1 strong floor to run kind of pseudodynamic testing or anything else like that. It's in the other lab, it's easy to go and see them. But then what we designed, conceived, designed, and constructed there was a testing rig essentially for isolation devices. Again, in San Diego, they had built recently some testing rig that was used for a project funded by Caltrans for very large bridges, isolation devices for very large bridges and so on. And well, I knew quite well all these facilities. I'd been teaching in San Diego in 1990 and so on. And clearly for me there, the problem was that the vertical load was very large, but the control of the vertical load was not enough. And controlling the vertical load is essential for certain kind of isolation devices, for example, for friction pendulum, where when you move horizontally, it goes up. And if you don't control precisely the vertical load, it's a disaster. So the rig that we had to test this kind of elements on the other side has a vertical capacity of 50,000 kilonewton, but it is controlled dynamically, the vertical capacity, and also the 2 rotations, the pitch and roll. And it's controlled at about 0.4 meters per second, something like that velocity, which is a high velocity because you should consider that you are testing something that has a very long period of vibration. Therefore, at long period of vibration, you never reach large velocities. Anyway, all these facilities had been, this testing rig had been somehow recreated in other places and so on. Then at a certain point, they come to, because Rui asked me to talk about this, but I need some story behind it. And when there was some possibility of having some money, and we constructed this facility, my idea was that we already know a lot about structure members, but we do not know that much about non-structure elements. So the idea was we need to have something to test non-structure elements. And there was one place, and this place was Buffalo, where they had something which was not like this, but similar, in the sense that this facility has 2 shaking tables, not one. The lower one, which is down here, which is this one, is a rather standard 6 degrees of freedom shaking table. It's moved by two diagonal actuators there and 2 diagonal actuators there that can control the 2 horizontal displacement and the rotation around the vertical axis. It moves on 4 flat actuators, pancake actuators that can only push, they cannot pull. So there are 2 long actuators, 2 spring kind of actuators that are somehow forcing the 4 on which the table is moving to enter halfway before starting the test, so that you use the flat ones to control the vertical movement and the 2 rotation around the horizontal axis, but you use them in more or less compression because they cannot go in tensile force. And this is just the lower shake table, this one. And I will not say that this is a reaction mass, which is about 40 times, and that this is isolated also in the ground, down in the ground, so on and so forth. But then the idea was to have another shake table, which is that one, the one that you see up there, which is in aluminum there, and is controlled by those 4 actuators. You see the actuators here. They have 2 meters displacement capacity and can control independently the 2 horizontal movements and the rotation around the vertical axis. The other 3 degrees of freedom of that shake table are controlled by this shake table. You see that they are connected with these elements here, and you see that this is a hinge and that one is a hinge. So the upper shake table has to move vertically like the lower one and has to rotate around the 2 horizontal axes like the lower one. In a way, what we could do there is to imagine that this is something between 2 stories of a building, any kind of 2 stories. Could be at the 40th story or at the 4th or anywhere. And we do not need to recreate the entire building to test something. Of course, we need some numerical analysis to define what should be the input down there and what should be the input up there. But in this way, here we can test anything that is passing through. You could test an elevator. We could test any kind of pipeline. We could test any sort of thing that is connecting 2 elements. And of course, the most obvious thing are just frames that are used as non-structural elements. And there are elements that are more sensitive to relative displacements, and there are elements that are more sensitive to acceleration at the bottom or acceleration at the top. There were a series of other problems. For example, you can see to the side those 2 towers, those white towers, and the reason to have something so impressive in terms of body is because we needed to have something whose frequency is completely outside the range of frequencies that you are using here. So those towers are around 70 hertz of frequency. But as you know, when you are increasing the stiffness, you need more mass. And when you are increasing the mass, then the square root of the mass divided by the stiffness maybe is not changing so much. So it's not easy to go beyond certain level of frequencies or lower than certain level of period of vibration. So this is the entire story of this machine. We do other things in this laboratory, but I think that I have to stop not to take too much time, and Igor will explain something about the test that is going to be run. The test will be short, so even if you spend even 3 minutes, you can do that.
Okay. Thank you. Thank you very much, Michele and Rui, for a perfect introduction. So I'm glad to introduce the test after these presentations. The test we are doing today on the 9D system. The test is on the specimen you see in the picture, and of course you can see here in full resolution here. So before describing the specimen, the 9D system has been used a lot in ERIES framework. Actually, is one of the 2 testing facilities we made available for the projects. And in the picture, you can see four pictures, actually, of the projects we have seen in the presentations these days. We tested masonry gables, masonry infills, ventilated facade and curtain walls, and industrial racks. The today test, as Michele was saying, this system is able to represent what is happening, not necessarily at the ground level, but what is happening along the height of a building or of a structure. So what we are representing today is actually the test of the seismic test that happens on a reinforced concrete building, 6-story building. The building is simulated, has been simulated both isolated at the base and fixed base. And what we are representing is now a system, a room-in-room system, which is located at the 5th floor of this structure. So basically, the 2 slabs are represented by the 2 shake tables we have here. The system is composed by a floating floor, glazed and opaque partition walls, and a suspended ceiling that maybe you can more or less see through the glazed. So the motion of the two tables is derived by the numerical simulation and then applied on the two-table system. In the base isolated configuration, we simulated a typical friction pendulum isolation system. Here we have some some specs of the isolators, so we won't discuss these details here. It's just to introduce the fact that we will carry out a test considering the isolated system and then the other ones with fixed base to see the difference. The seismic motion we consider is the earthquake that happens in Norcia, Perugia, Italy, during the central Italy earthquake sequence, a very destructive earthquake that struck the central Italy regions some years ago, 2016. You can feel now the noise. The plant, the hydraulic plant, of course, is now in pressure. Needed to launch the test. You can feel some noise. This is the foreseen test sequence. We'll have the first run base isolated, and then the other ones at different scaling with fixed base. Let's see what happens and at which level the specimen will show us some damage, something. So this is the first test run. Andrea can switch. We can switch on one of the screen of the controller. Okay, so the first test, base isolation configuration can go. Few seconds before going to check all parameters and everything. As you imagine, it's not something you just push a button and everything is okay. So better to take some time to check what is happening. Okay, test is starting. So this was the first run. As we expected, likely enough, the base isolation system supposed to work, and actually, even considering we are at the 5th floor, we didn't get much displacement. So the guy inside the room is still working and probably just realized that something happened, but nothing to worry about for the time being. So that's what we expect. I didn't mention, sorry, that the graph you are seeing on the LED wall is one of the 3 screens of the control system. In particular, you can see in the bottom from left to right X and Y displacement of the shake table at the bottom. X is this direction, Y is toward you. And on the upper part, again, X and Y of the upper shake table. So, few seconds, we can switch back to the presentation. So the PGA we had simulated at the base of the building was 0.26 G. You see that what we, we got at the 5th floor is even a slightly lower acceleration. Again, something we're expecting considering a base isolated structure. These are some displacements just to give you some results. This was scaled at 70% of the original record. Now let's switch to the fixed base configuration, in which we will go ahead increasing the seismic intensity and see what happens. To start low, we will start from a lower percentage. This will be the original record scaled at 30% of the intensity. So when in the control room they are ready, we can again start the run 2. This is quite interesting to notice, actually for 2 reasons. Well, first, that already at 30%, we already have some more acceleration and displacement respect to the test 1. The second, actually, is that the front, the central glass, is not supposed to be a door opening so easily. So something that in the installation phase maybe is not immediately visible can turn out to be in an earthquake scenario. So something is happening and we are realizing. But that's evidently what can happen in reality. So what we got now, again, a couple of graphs, but won't spend much time on this. See the acceleration start to increase already from respect even to the previous case, and also absolute and relative displacements start to increase. Now we should allow maybe, I don't remember if already now or after the next test, we need to allow a couple of minutes for the plant pressure, for the pressure to go at the highest level is used, typically is 280 bars. This is needed for the most intense testing, which the accumulation system has to work not maybe 100% from this run, but maybe it will be needed later on. So this process takes some time for the accumulator to be filled with the oil. So next one will be 50% of the original record. Don't know if they are ready. Okay, so let's go for the next run. Okay, already something even more than expected. We didn't carry out analysis on this specimen. Past occasion we had something similar that needed some more energy to be severely damaged at least. I don't know, maybe if we can move a couple of elements there and keep going with another run. So, in order to go ahead with another run, even if we already got some serious damage here, well, let's take advantage of the specimen. We can go for another run. I will ask you just a few minutes to wait. We will just take out a couple of elements over there because they will disturb a bit. But to do that, we need to lower the pressure on the shake table to safely jump on it and work and remove this, this element. So after that, we'll go ahead with another run. I'm expecting that we are not going much further than this, but we'll see. This is part of the research process. So for those of you that are not very familiar with shake table test, you know that normally this kind of test with maybe 3, 4, 5, 6 runs generally takes 3 to 5 days. We are trying to squeeze this process in half an hour and have everybody happy and ready for dinner. So I can ask you, I will ask you to wait few minutes. It's much less anyway than a normal standard project, let's say. In the meantime, I can show you a couple of graphs what kind of acceleration triggered this damage. Actually, it's something still interesting. So we are talking now about an acceleration that was at the top level something like 0.5 g, slightly less on the x direction, and even a bit less on the y direction. Of course, displacements are getting already quite high. Imagine that here, since we want to represent what is happening at that level, and we need the absolute acceleration to trigger the damage to see actually in real conditions what is happening to the specimen. So we need absolute accelerations and relative displacements as well. So, of course, displacements are getting quite high and quite early. We are not talking about just relative displacement to the base. The guy inside the room is still working. He's not, he's not scared for the time being. But he's used. Actually, that guy in particular, I've seen quite a lot of tests, real tests, research tests, demonstration. So he's well trained and he's still not worried at all. Thank you guys, very fast, like Formula One technicians. We have the best. Okay, so again now, let's allow some time, few minutes, 2-3 minutes maybe, to raise the pressure again before going to the next run. So next run we'll make a jump from 50% to 100%, so double the intensity we have seen now. So I'm expecting something can happen. The glasses you already have seen, actually, they have a film inside the two glasses, so they are not supposed to explode, but to, let's say, gently collapse. This is what is happening so far. I think we have quite enough distance for the time being. But yeah, we'll expect that something more will happen. Few seconds again to make all the accumulators being filled. The reason why maybe I'm saying something quite common for shake table familiar research, but accumulation system is needed to cover the highest peak of displacements and velocity of the shake table, why the regime of the pumping system cannot cover such amount of oil flow required in a short time. So that's why those systems are basically all made of a pumping system and accumulation system to supply, to cover this highest oil demand. Okay, from the control room they are telling me they are ready, so 100% of the intensity, something more will happen. Let's see. Okay. I think we had in the pocket a couple of run more. Never know that maybe the performance required was not this one, but I think that yeah, we got some interesting results and some work to do for the guys till the end of the shift. Okay, so I think this was it. Maybe we're a bit late, but even not that much, probably. Maybe we recovered some time. So thanks again. Hope you enjoyed. If you have any question, curiosity, or everything, I will be available, and Rui and Michele will be as well. So thanks again, and thank you very much. And see you at the dinner later on.
I'm looking for Gerard. Gerard, where are you? Because there's now a General Assembly, and okay, Gerard is already in the General Assembly room. So the General Assembly room is the multimedia room where the wind engineering parallel meetings were taking place. So those that are members of the General Assembly, those that are members, if you do not know if you are, it means you're not. So those that are members of the General Assembly,